Hello, welcome after a break. Today we shall study a very important aspect of earthquake engineering. The topic is response spectrum, concept and construction. Response spectrum is a very core idea in earthquake engineering for design purpose and for analysis purpose. So let us see what is the background of response spectrum, how it is constructed, what are the standard expressions related to the concept and so on. Let us consider one spring having stiffness K. We apply a force Fs for extending the spring downward, and the spring extends by an amount U displacement. So the force stiffness relationship is very simple, Fs equal to K into U, that is known to us. Now let us see one thing, the peak displacement, what does it mean? So we have considered one structure, a cantilever structure, and subjected to a lateral force Fs from left. It undergoes a displacement U and it has a stiffness K. Now for equilibrium there is a force acting from the right hand side at the base, and this we are calling as base shear. Base shear and Fs will be equal. So we have already seen Fs equal to K into U, and we know omega equal to K by M under root, the frequency of the vibrating system. So this gives K equal to M omega square. So equation 1 can now be written as Fs K into U. We shall write Fs M omega square into U, and omega square U let us take together within parentheses. So the maximum value of the Fs will be at the point when U is maximum. So then in that case U become U max. So Fx max equal to M omega square U max, and this U max let us denote by a symbol capital D. Then Fs max equal to M omega square D. This omega square D let us define by another parameter capital A. So Fs max equal to M into A, where A equal to omega square D. With this substitution, it is found that this A has the unit of acceleration, and this is called as pseudo acceleration. Omega equal to radian per second square. Radian you can say has no unit for the timing, and so D is displacement. So it becomes displacement per second square, which is nothing but acceleration. It is not true acceleration U double dot, but a kind of acceleration having the similar unit, and that's why it is called pseudo acceleration. Similarly, we have another term, the pseudo velocity. Let us see how it comes into picture. Kinetic energy is equal to potential energy when the system is at the peak displacement point. So in that case, you can write K equal to half Fs into U. Fs into U is the half Fs into U is the strain energy, and Fs we are substituting by Ku, so it becomes half Ku square, and K equal to M omega square that we have seen. So we can write half M omega square U square, and taking omega square U square together, we can write half M omega U whole square. This omega U, when we consider the maximum kinetic energy, that is Ke max, in that case U becomes maximum displacement U max. So Ke max equal to half M omega U max whole square, and this you can write equal to half M omega D whole square. This omega D we want to express by a new variable V. So we can write Ke max equal to half mv square. This is looking very much as the kinetic energy in physics, and so this is the this V is called pseudo velocity. So V equal to omega D. It has the unit of velocity because omega equal to radian per second, and radian you can imagine not having any dimension, so it is displacement D by second, that is velocity. So this is not the U dot exactly, but it is similar to that, having same dimension as that of velocity, and it is called pseudo velocity. So we are getting now three parameters here. Capital D we have used for peak displacement, peak value of the displacement. Capital V we are using for pseudo velocity. This is also for a peak condition because we have taken kinetic energy maximum. And A we have taken as pseudo acceleration, the peak value of the acceleration, because we have considered also peak value Umax in that case. So these three parameters are also expressed in spectral terms. What are these? SD, the spectral displacement, SB, spectral velocity, and SA, spectral acceleration. What is spectral? Any graph that is plotted with time period or frequency in the x direction and some parameter in the vertical direction is called a spectrum. So from the word spectrum, the spectral term comes, and we have the three varieties of spectral parameters: spectral displacement, spectral velocity, and spectral acceleration. All these will be having their utilities depending on the cases, and we'll see how they are expressed. So what is the definition of a response spectrum? Response spectrum is the graphical presentation of some peak response quantity of a series of single degree of freedom systems with varying time periods for a particular damping under a given earthquake. So definition is slightly lengthy, and it has so many terminologies inside which are having their particular meanings. Let us take these terminologies. Peak response, then single degree of freedom system with varying time periods and a particular damping, and it is under a given earthquake. So one by one let us see. Peak response can be the peak displacement response, or peak velocity response, or peak acceleration response. Now all these parameters can be positive or negative based on the time. For causing destruction in the system, the positivity and negativity will not matter. It is the magnitude that will matter. So we take the absolute values of these peak responses. Peak displacement, peak velocity, and peak accelerations will be always positive because we shall be taking the absolute value for the parameters. Then single degree of freedom system means it is having a single mass m, it has a stiffness k, and it has a damping associated c, or you can express through xi percentage. Then varying time periods, the time period will be t1, t2, t3, and so on. We are expressing this by ti. And this response spectrum will be valid for a particular damping. So it can be 5% damped, 10% damped, and so on. So damping is to be mentioned. If you change the damping, the response spectrum curve will change. And it is under a given earthquake. For each earthquake, there will be associated response spectra, the displacement response spectra, velocity response spectrum, and acceleration response spectrum. So when you change the earthquake, the response spectrum will change. When you change the damping, response spectrum will change. Now how the response spectra look like is given in this slide. The first one is showing the displacement response spectrum. So as we are taking the absolute values, so negativity is not coming into picture, so it does not go below the x-axis. It is always positive values. So these are the response peak displacement values for a particular single degree of freedom system. So this curve is for peak displacement, the second curve is for peak velocity, and third curve is for peak acceleration. So these are different response spectra for some particular earthquake. Now what is the meaning of this diagram? Let us see. Let us take 1 second as the time period. So 1 is here. Corresponding to 1, we have the peak displacement 5.97 units, peak velocity 37.5 units, and peak acceleration 0.610 units. So the peak values of those corresponding parameters can be read out once we know the time period of the system. Now there is one inherent knowledge that we should know while making the response studies on the response spectrum or constructing the response spectrum. So this is time step analysis, which is also known as time history analysis. The time history analysis we discuss here in brief because this will be utilized in making the response spectrum construction. The time history analysis goes step by step on the time domain. So you take a very small time step size, maybe 0.005 second, and consider the equilibrium of the system. So applying the equilibrium system, you can get a solution of the structure in the current time step. With this knowledge, you interpolate it to next step and again set the equilibrium and the dynamic equations and get the solution for this structure for the next time step. So this way, step by step it will proceed, and there will be thousands of time steps in the solution. In every time step you are getting all the response quantities, not only displacement, velocity, acceleration, but also bending moment, shear force, and all parameters for a structure in the time history analysis. There are many standard methods available for time history analysis, like Newmark method, Wilson's method, a central difference method, and so on. In Newmark method also, more internal variations are there, like linear methods, non-linear methods, and so on. So let us see in brief the time history analysis, how we carry it out, the steps. There are two constants in the Newmark method. We are particularly taking Newmark method. There are two constants, beta and gamma, which can be chosen from the literature. Typically they are 1/4 and 1/6. The equation of motion is mu double dot plus u dot plus ku equal to f, where u is the displacement parameter, and other parameters having the standard meanings: mass, damping, stiffness, and right hand side is a dynamic force, time varying force. So we take the step size delta t for the purpose of computation. Then we find out some parameters, the effective stiffness. The effective stiffness given by k bar as shown here is equal to normal stiffness, then a part decided by the time step size, gamma, beta, and c, and another decided by the mass and beta and delta t. So this gives the effective stiffness. Then there are two constants a and b, which are to be calculated through this formulae as shown here. Initial acceleration is given by the equilibrium equation itself. If you take this u double dot on the left hand side and remaining things you take on the right hand side, you get this equation. F naught and u naught dot is indicating the initial when the time period is 0, initial point where time is 0. So initial amount of acceleration can be obtained from this expression, and that is derived from the equation of motion given here. For one time step, the computations are like this. You find out the effective force, which is the increment in the applied force, this F which is given, or Ft, its increment in a current step, that will be known. So that is the increment, and then based on the velocity and acceleration of the previous step and the constants a and b, this effective force can be calculated. So the displacement in the current step is effective force divided by effective stiffness, which was found here. So this gives the displacement increment. Similarly, velocity increment is given by this equation that can be found out, and the acceleration increment is given by this equation given here. So after one time step size, you find out the resultant parameters. Ui plus 1 for the next time step is equal to ui plus delta ui. Similarly, for the next time step, ui plus 1 dot or u dot I plus 1 equal to u dot I plus delta ui dot. Similarly, acceleration, u double dot I plus 1 equal to u double dot I plus delta ui dot. So now, from the knowledge of the previous time step, we have found out the response parameters, displacement, velocity, and acceleration for the next time step. Now set I equal to I plus 1, that is increase this time step number and go to the step 1 and repeat all the process again. So if you repeat all this process, you are getting this, you see here the displacement in different time steps, velocity in different time steps, and the acceleration in different time steps. So you get the histories. One history is ut, displacement history, and velocity history is u dot t, and acceleration history is u double dot t. So if we consider the maximum value out of this displacement history has many values based on the time values. So out of that, the peak value we can find out, peak absolute value, and that peak absolute value we can call as u max or capital D. Similarly, velocity will have the u dot max or the v, pseudo velocity, and the acceleration u double dot max or a, the pseudo acceleration. Though the u double dot is not equal to a exactly, and u dot is not equal to v exactly, but as we are going with the peak value of d and derive to those values with omega d, omega square d, etc., we got these peak values of velocity and acceleration in the form of spectral or pseudo values. Now in the response spectrum construction, those time history steps will be required. So the data supplied are the earthquake that is given, then percentage damping or the damping coefficient is given. Set I equal to 1, consider a single degree of freedom system with time period Ti or T1 and with the damping that is given here. Now subject the system to given earthquake and apply numerical time test step analysis to evaluate the response ut, displacement response. Obtain the maximum absolute value of the ut and name it as di equal to max absolute ut, absolute value of the displacement maximum. So we get this point now, Ti for the current step number I, you get Ti, and the peak displacement after carrying out the time history analysis is di. So Ti di is one set of points which will be coming to our response spectrum construction. Then set again I equal to I plus 1, that is you increase the step size number and go to step 1 and repeat this process until a desired number of steps are available. So now with this process that we have applied, the biggest process in the step 2 where you are carrying out the time step analysis. So here time step analysis is carried out fully and you get the ut response that we have discussed in the previous slide. Out of the ut you get the maximum peak value, that is di. So at the end you have series of Ti di values, I equal to 1, 2, 3, 4, etc. So along the horizontal axis you take the time period Ti, and vertical axis you take the parameter of interest. We have shown here di, so it will be displacement response spectrum, but instead of this di you could have taken vi or ai, so that it could be velocity response spectrum or acceleration response spectrum. For velocity response spectrum, capture Vt in the time step analysis and obtain Vi max absolute Vt. And for acceleration response spectrum, capture the At in the time step analysis and take Ai equal to maximum absolute At. So from this same time step analysis, you get all the required displacement parameters di, Vi or Ai. Now we have the spectral quantities d, v and a, which are given by this v equal to omega d and a equal to omega square d. So they are simply related by this expression a by omega equal to v equal to omega d. Okay, so from this expression we get this, where omega equal to twice pi by t. This, if we take logarithmic relationship with, there are three equations actually, a by omega equal to v, a by omega equal to omega d, and v equal to omega d. So three equations are available here. So we can write log a minus log twice pi by t, because omega equal to twice pi by t equal to log b, and log a equal to minus log twice pi by t equal to log twice pi by t equal to log d. When you take a by omega equal to omega d together, you get the second equation. And when you take b equal to omega d part, then you get log b equal to log omega, that is log twice pi by t plus log d. So now we can plot a logarithmic curve for the response spectrum instead of normal ordinates, and it will look like this. It is a tripartite log paper, that is logarithmic scale is there on the x-axis, y-axis, and also in some other axis which is inclined with the x-axis. So one axis is taken in appropriate location inclined at 45 degree, and another axis is taken at 135 degree. Now how to read this tripartite log paper value? Consider any time period, say 2 seconds, and go to this diagram, the tripartite log diagram or tripartite response spectrum. You reach here from the time period 2 seconds, you reach here. This axis which is inclined at 45 degree with the x-axis is the displacement axis d, and the axis which is inclined at 135 degree with the x-axis is the acceleration axis, this one. So from this point at 2 seconds, you make a perpendicular to the displacement axis, and this gives you the displacement, peak displacement corresponding to that time period. Similarly, if you draw a perpendicular to the acceleration axis, then you get the peak acceleration corresponding to that time period 2 seconds. If you want the maximum velocity or zero velocity, then you simply go horizontally to the v axis, and the value you get here for the peak velocity. So the beauty of the tripartite log paper is that from the same graph you get all the three parameters: spectral displacement, spectral velocity, and spectral acceleration corresponding to any time period. Now the single degree freedom system is to vary with this time period. That is, time period has to vary from some value to a higher value, and you need to make the time history analysis for all these time period values one by one. So for that purpose, the background work is like this. You consider the equation of motion mu double dot plus u dot plus ku equal to ft. Divide this by mass m. So if you divide, we get u double dot plus c by m u dot plus k by m u equal to ft. Now from dynamics we know c by m equal to twice omega xi. Xi is the damping ratio, omega is the frequency. Then k by m we have seen in our previous slide, omega square. So omega square u equal to ft by m. And omega equal to twice pi by t, so substitute this here in all the equations. So u double dot into 2 times twice pi by t xi omega dot plus twice pi by t whole square u equal to ft by m. Now in this equation the time period has got involved, so we can change the time periods and plot the carry out the time history analysis for different time periods. In the standard time history analysis, we have seen the standard equation of motion, this one. And in our modified time history analysis equation and modified dynamic equation, we have incorporated the time period in the parameters, so that we can simply vary the time periods and carry out the time history analysis for each time period and get our peak responses. While solving by numerical technique, we note that in this case, coefficient of u dot is now unity, as seen here. Initially in the standard dynamics equation, coefficient of u dot was m, but in our converted equation it is unity here. Coefficient of u is here, u dot is this one, 2 into twice pi by t xi, which was earlier c. So in the time history analysis, wherever c is appearing, you simply substitute by this parameter. Similarly, coefficient of u is twice pi by t whole square here. Earlier it was k. So wherever k is appearing in your original time history analysis formulation, you use this one, twice pi by t whole square. The right hand side will not change, m will not be unity here, it will simply be ft by m actual. So right hand side will be like this. So now you can go back to your original dynamical equation. With this substitution of the value of m, value of c and value of k, and right hand side is equal to ft by m instead of ft, you can simply carry out the time history analysis as per standard procedure and get the response parameters. The displacement response history is like this, having less zigzagness, and it is always positive, it is above the horizontal x-axis, time period axis. The velocity response spectrum is having more zigzagness, it is also always positive, and the acceleration response spectrum is having the maximum zigzagness, and all the values are also positive here, remaining above the horizontal axis. Horizontal axis is time period, so corresponding to the time period we read out the parameter of our importance or of our interest. Now in the Codal base shear there is a formula Vb equal to etc. that has been derived from the basic equation as here. Now Vb equal to Fs we have seen in the beginning slides, and that was finally written as m into a was pseudo acceleration. So pseudo acceleration is also called spectral acceleration, SA. So we are writing Vb equal to m into SA. Now m equal to w by g, weight by g is the acceleration due to gravity, so we can write it like this. Now we rearrange this SA by g into w. So you get actually Vb equal to SA by g into w is the basic base shear equation coming out of dynamics and coming out of the concept of response spectrum. This basic equation has been modified by the code. This is the basic equation part. This has been modified by the code to accommodate other things. What is the things accommodated? Z is the response spectrum, zone factor Z, which gives the seismicity level of a particular area. So that one diagram and one formula can accommodate all areas in the country, in India. So Z takes care of that zones. And I is the importance factor, the importance of the structure. Some structures will be more important, like community hall is more important than residential building. So that way importance factor comes into picture. 2 comes into picture from the concept that we design for the peak value of the acceleration that is possible in a zone, but half of that, because the peak may not actually happen in the lifetime of the structure. And R is the response reduction factor, which is used to accommodate the non-linearity, damage and ductility of the building. So our Indian codal response spectrum is like this, and in other countries also the design spectrum are more or less of this pattern. So these are typically drawn for 5% damping, 5% damped spectrum, because for concrete build system the material damping is 5%, and these are elastic systems, elastic response spectrum. Now what is the relationship between the response spectrum and design spectrum? For drawing the design spectrum you need the construction of large number of response spectrum in a country. Okay, large number of response spectrum. So say I take 500 response spectra for different 500 earthquakes which took place in the past or which can be synthesized through some software. So each of these earthquake will have their corresponding response spectrum. Acceleration response, here in our code acceleration response spectra is given because the particle axis is acceleration axis. So if you take 500 response spectra or 500 earthquakes and take an average of all these, then it becomes the design spectrum for the country. That way, and then you have to smoothen it because that curve may not be smooth. So you can take average and then smoothen it, then it becomes the design spectrum. And in the Indian condition, for 3 types of soil, 3 design spectra lines are given. Now there is one concept called the inelastic spectrum. What is that? So far the response spectrum we have considered, the single degree of freedom system was linear. That is, non-linearity was introduced in the behavior of the single degree of freedom system. It was that Fs equal to k into u, it was elastic, a straight line. But if you consider that the single degree of freedom system is getting damaged at some point and it is becoming non-linear, then the resultant response spectrum will be called as inelastic response spectrum, and they will be not simple as earlier, but a lot of zigzagness and curved nature like this. So this is the inelastic response spectrum drawn for inelastic behavior of this single degree of freedom system. The single degree of freedom system in the nonlinear condition, the simplest one is the elastic perfectly plastic response. That is, it is straight line in the beginning, then horizontal. It can be also bilinear, it can be multilinear, it can be curvilinear. So if you consider all those nonlinearity in the behavior of the single degree of freedom systems in constructing the response spectrum, then that response spectrum will be called as inelastic response spectrum. Another example is given here, inelastic response spectrum for different earthquakes. Design spectrum, as we discussed, and several response spectra are drawn, as we said. Then you can get an average of the response spectrum and then smoothen it, then it becomes the design spectrum. It can be shown in the tripartite log paper also. So you have drawn large number of response spectra in the tripartite log paper and take average of all these and smoothen it. You get a curve like this, then that will be the design spectrum in the tripartite log paper for that area. Now there is a concept what is called site spectrum. So for important projects like say nuclear power projects, for dam and like that, the design spectrum of the code is not sufficient. Why it is not sufficient? Because design spectrum of the code is given for a vast mass area. A big zone is given for one zone, big area. And in that area there are a lot of variations in these seismic actions. So for your important projects, that average will not work. So you take site specific information and construct the response spectrum for that very site only. So you need to get the entire geological data, entire seismological data, nearby faults, distance of the faults, and then soil properties and so on. And from that, using the appropriate knowledge, you can construct the spectrum for that site, which is called site spectrum. Now when you design the structure for that site, you shall be using site spectrum instead of the design spectrum, so that the structure will be safer and with our full knowledge. Similar term is average floor spectra. What is that? When you have to design an equipment, this base of an equipment, the foundation of equipment resting on the floor, then the design spectrum of the code will not help, because design spectrum of the code gives the effect of the shaking in the ground. But your equipment is getting shaken at the floor level. So what we do, we consider the acceleration history of the floor and consider it to be an earthquake. And then apply single degree of freedom system standing on the floor and get the response spectrum out of that floor acceleration spectra. And what you get is the response spectrum for that floor only. So you can get for several earthquakes, you can get the response spectra for the floor and take the average. And that can be used for design of the machine foundations resting on the floors. So it is shown here diagrammatically. We have a building here and an earthquake is taking place at the base of the building. As a result, the floors are getting accelerated and they have their own acceleration response history. So that can be obtained through time history analysis. So now this is an earthquake which is taking place at this floor level. And any earthquake has its corresponding response spectrum. So I can draw a response spectrum of this earthquake and get the spectrum, response spectrum, which will be the response spectrum for the floor. So we have drawn the acceleration response spectrum for the floor, and we have considered several earthquakes here one by one, so that we got several response spectra for the floor, and you can take an average of all this and use that for design purpose for the foundation of the equipment resting on the floors. Thank you very much. Please subscribe the channel, like the videos, and put your engineering inquiries in the comment box. I shall be glad to answer those. See you again.